Good morning to everybody. This is my presentation. You can see the title, Learn Evidences Experimenting with Hydrogen and Deuterium Loading in Thin Palladium Films. I started to work on this experiment I will present you about 2 years ago when Mizuno published the first results with the reactor, if I am correct, R19. So I couldn't work continuously on these experiments because I have 9 grandchildren. So, and while I am retired from my company, my ex-company, I need to take care of grandchildren. So this is the outline of my presentation. Previous finding, reference, setup, overview, palladium electroplated nickel sample, loading, monitoring, neutrons and heat, final conclusions. Okay, here there is the web address of the site of Argal organization, Argal research organization, and you can see I put in the website 3 files recently just to complete what I am presenting now, because the presentation in this contest is very short. It's just a summary of what I did in these 2 years of work. So you can take a look to previous work, going to the what is indicated by the arrows in this Argal page. It's possible to see. Okay. This is the setup overview of my one of my reactors I have in the lab. The reactor is a stainless steel chamber with a volume of 320 cc, and I have in the lab a continuous monitoring of gamma emission, making a gamma spectrum each hour. And I have also neutron monitoring continuously working in the lab. Right now is in function. There is some interface to collect data in a computer with a LabVIEW program. And on the back is not usable very well. There is a hydrogen generator, is an electrolyzer for very pure hydrogen gas. Okay, what is important in this experiment, I realized just during the experiment itself, the pressure monitoring, because something happened that was unexpected when I prepared the experiment. So I have Edwards sensor for the temperature and the interface to the computer, and this the display monitor. This is the sketch of the reactor when where I put inside the material to test. In all my tests, I have a palladium resistor, a thin film palladium resistor, just to verify that the atmosphere inside the reactor is the correct one. And this resistor is 5 ohm resistance, is a thin film, and it's important because I can verify the dynamics of the absorption of the hydrogen or deuterium inside the palladium. Below, inside the reactor, there is also a heater. There's a 1 ohm heater, is a resistor, and there is a dielectric plate to separate the material from the resistor, from the heater. And on top of this ceramic insulator, I put the material to test. This is some picture about the first experiment done about 2 years ago, when I knew the work done by Mizuno with nickel and palladium coverage. I was suggested in some paper of Mizuno that you can put palladium on nickel, also electroplating the material. And so in my lab I was able to make this kind of deposition, because I did in the past experiments on co-deposition on palladium of nano palladium to see alpha particles. And so I used the same chemical solution to make electroplating of nickel foam of small dimensions. The first experiment was on about 2 square centimeter sample. And in that experiments, I just was able to find neutrons emission, not heat was produced by that experiment, also using hydrogen or deuterium. Then recently, I repeated the experiment, putting inside the reactor higher quantity of material, about 0.5 grams of nickel foam. This is in the center of the screen. You can see the sample. The diameter is about 4 centimeters, and the weight was very low. On the right side of the slide, you can see 2 curves. The black one is the pressure inside the reactor, from 0 to about 1 bar, 950 millibar. The red line is the resistance of the monitoring resistor. That goes from 5 ohms about to 7.5, something like that, with a hydrogen. On the left side of the screen, you can see the behavior of the pressure in the chamber. The red line is the temperature inside. Is the value of the resistance of palladium, stable, because it reaches the equilibrium with hydrogen very, very quickly. And in few minutes, 2-3 minutes, reaches the saturation value. And the graph, the x-axis, shows the time. It's not viewable so well, but the white line is the pressure inside the reactor. And this decrease of the pressure lasted 3 days. Was the first loading of the hydrogen into the chamber, and I was surprised to see after half an hour, 1 hour, a small decrease of the pressure. So I let the reactor stay there, And I waited, and I saw in the next days that the pressure was decreasing slowly. And okay, you can see some irregularity in the decrease of the pressure due to the environment temperature. When the environment temperature is moving, during the night it's cooler, and you can see some variation in the pressure. Okay. So after this absorption of about 80 millibar of decrease of the pressure, I was stressing the material, heating it and making vacuum inside the reactor to see what if the mechanism will be repeated in the next filling of the reactor. And this is one of the filling, the subsequent filling of the reactor. And you can see, in this case, the x-axis is each line, each square is half an hour. So the decrease of the pressure was more rapid than in the first loading. And you can see on the right of the slide the variation of the temperature of the sample. On the sample there is a small sensor for the temperature, is a very small PT100 sensor, and you can see that sorry, the temperature of the sample increased during the rapid decrease of the pressure, and the increase of the temperature was of about 1-2 degrees, not a big amount. And after that, I made again vacuum the reactor. I heated the sample to absorb the hydrogen, and then I filled it again the reactor with hydrogen, and I saw that the mechanism repeated again after about 2 hours after the filling. After 2 hours, we had a quite rapid absorption, and again, the chemical increase of the temperature was clearly visible in the computer. Okay, the amount of absorption calculated by calculating the volume of hydrogen absorbed was quite interesting just after the first absorption phase. And the total amount was 58 cubic centimeter, and the ratio between hydrogen and nickel was 0.6, quite new at environment temperature. I was aware that in the previous experiment I stressed the nickel in hydrogen without palladium, and I had absorption only over 150 degrees, but not so big absorption, very smaller. Okay. And during some period of hydrogen in the reactor and this kind of material, making subsequent filling, I observed during a steady state of the reactor some neutron emission in hydrogen. Neutron emission, normally I had many times this kind of emission, but in form of burst, not very prolonged emission of neutron, even if very small over the background emission was observed in the first experiment with the palladium only or palladium over meter. The overall amount of hydrogen absorbed, making subsequent filling after the absorption, was such to have a total absorption of 112 cubic centimeter of hydrogen. The value, the ratio between hydrogen and nickel is calculated as 1.18. Okay, this is the graph, the monitoring of the neutrons. The green dots are relative to the upper x-axis, means neutrons per hour. And you see that in the hour 11, I had 17 neutrons in that hour. 17 neutrons. And it means that that point is really out of the background distribution of the neutrons detected that we can observe here. This is the histogram of neutrons per hour compared with the background in the dotted line. And we have the point with a burst of neutrons, not so big, by the way, and 17 neutrons in 1 hour. It is very far from the normal distribution of the monitoring. The background is coming from a lot of acquisitions, 1,000 acquisitions, even more. And heat excess after D2 loading. This was quite unexpected, like the abnormal absorption of the nickel. And at a certain point, I stopped to use hydrogen inside the reactor and try to put deuterium. And you can see the loading of deuterium. You can follow the loading of the monitoring resistor is the white line in the left of the slide. That is not the resistance, but is the power dissipated on the resistor. So when the resistance increases, the power decreases, and you can see that at the end of the absorption of the monitor resistor, I had the red line is the temperature of the sample. I had an increase, a small increase of the temperature of the sample just when the monitor resistor saturated. And you can see the first jump of temperature was only a few degrees, 5, 7, 10 degrees. But after that, the grid is 5 minutes each line. The grid of the x-axis is 5 minutes. So we had for 20 minutes the temperature of the sample went up and down and reached the maximum value of 130 degrees without any energy inside the reactor, inside the sample. So the dynamic of the deuterium absorption is indicated by the white line in the graph. When the absorption reaches about stability, I had this maximum temperature increase. And this was unexpected, and I suppose that there was something wrong with the reactor, because maybe that the connection of the PT100 measuring the temperature on the was not stable. And this effect, I took a picture. This is a picture from my phone. I took a picture just to memorize this event, but I wanted to wait to make conclusions when I will be able to extract the material from the reactor. And so, okay. The thermal anomaly begins, as we saw, in coincidence with the end of the D2 absorption in the palladium. The thermal anomaly, if true, must be attributed to an exothermic reaction in the palladium or at the interface with nickel. Given that the continuation of the experiment for days did not show any absorption of deuterium in the nickel. That is quite strange. Differently from hydrogen, no absorption of deuterium into the nickel. During the thermal anomaly, gamma and neutron recording remained at the background level. No. This is the thermal model of the reactor. So it is quite easy to measure the thermal resistance between the material to the chamber, from the chamber to the environment. So we could calculate the maximum power produced during the high jump of temperature. This thermal resistance are measured at a steady state of the reactor. So it's quite easy to, the value R1 plus R2 is 14 degrees per watt. And so the maximum power produced in the sample was 7.1 watts minimum, because you need to take care of the charge of thermal capacitance. Unfortunately, the thermal capacitance to the environment and the thermal resistance to the environment are determine time of stability of the chamber of 5 hours. So while the increase of the temperature of the sample, if you have power, takes minutes. So I will analyze the raw data of that are stored in our disk to see if also the chamber had an increase, a small increase of temperature, but I didn't have time to do that. So after this event, I suspended my judgment to wait to extract out the material to verify the condition of the thermal sensor. I did that after weeks, and I confirmed that everything inside the reactor was stable. So the connection of the PT100 to the measurement tool was correct, was stable. And also, continuing the experiment, the thermal sensor didn't give me any problem. So it was working as usual. After getting out of the deuterium, I was able to put hydrogen again inside before getting out of the material. And there was, I had again cycles with good absorption, but cycle after cycle, this absorption disappeared. And when I took a look at a microscope, optical microscope, to the sample, I saw the lamination of palladium deposited on the nickel. So there is no any more absorption at environment temperature. Okay, I tested also titanium to do this kind of test, but I had absorption only over 150 degrees. I get titanium foam is different from nickel foam. It's much heavier in the weight is higher. And I had a moderate absorption only on over 150 degrees. Conclusions. Okay, the unexpected ability to absorb a hydrogen at room temperature by a sample of nickel on the surface of which a thin layer of palladium was deposited could be exploited to activate LENR anomalies. In the specific, in one experiment, the volume of H2 absorbed by 0.5 grams of nickel was about 112 cubic centimeters, such as to bring the ratio between hydrogen and nickel atoms to a value around 1.18, higher than the threshold considered for the activation of the LENR anomalies in the palladium. As for the other experiments in neutron emission burst is associated to hydrogen and deuterium metal loading. Even though D2 did not show absorption in the nickel, a clear episode of excess heat generated occurred at room temperature, of which the activation mechanism remains still undetermined. This is the next possibility we have to make a real replication of M2U00137 experiments with my friends in the Arcal Association. Thank you very much for your attention.
Thank you, Ubaldo. Questions? Here's one in the front, please.
Thank you for your work. Did you use about deuterium cycles? Some cycles with only hydrogen before, or you change your samples and using you made full cycles only with deuterium.
Sorry, I lost the first part of your question. Could you repeat?
Yes. Your first tests are made with only with hydrogen cycles. Then you made the same with deuterium cycles. About deuterium cycles. Okay. Sorry. Thank you. About your first cycles by hydrogen. You don't have any excess heat, I understood. Then you tried to make the same with deuterium by several cycles to load the deuterium. But in this case, did you make the first cycles with hydrogen, then you add some cycles with deuterium to add some excess heat?
I really don't understood your question.
Let's see if I say. You were asking if I'm right.
So you started first with hydrogen, and you didn't get any excess heat.
Yes.
And then you heated up to below the hydrogen.
Yes.
To what temperature? First question. And then you loaded with deuterium.
Yes.
And then you got this excess.
Exactly. Yes. That's all.
Okay.
Is that satisfactory?
What is different from hydrogen and deuterium? With hydrogen, no excess heat. With deuterium, excess heat, but no absorption.
Okay.
The absorption was only in the palladium. I had the monitor of the absorption of deuterium into the palladium. Maybe that all the tests I did prepared the interface between palladium and nickel in a proper way to make something activating the reaction. Because as you could see, we had a very different absorption from the first loading to the subsequent loadings. So the interface changed during this many experiments.
One last question of this talk, please.
Last question.
One more question. Yours.
Okay, this is very much probably linked with what you're
Voice,
discussing now. Very much linked with what you're discussing now. In your conclusion page, there is an expression, the unexpected absorption of hydrogen by nickel. Yes, it normally means that quite strong conditions are required normally, like high temperature and high pressure for nickel absorption.
Yes.
And you are now explaining why nickel is absorbing hydrogen at room temperature in your case. Maybe you can explain once again why and how you calculate this amount of absorbed hydrogen. This is my second question.
I can tell you my opinion about what happened. You have the palladium absorbing hydrogen, and at interface there is a situation like able to pump hydrogen from the palladium to nickel. And this is due to what potentials, different potentials, chemical potentials, I don't know exactly, but is clearly some mechanism happening at the interface from palladium to nickel.
And how did you evaluate the amount of absorbed hydrogen?
Very simple.
Let me ask you to talk privately because there are a lot of details. Your questions are good. You want to respond now?
Yes, I measured the quantity of hydrogen disappeared from into the chamber because the pressure decreased a lot. I measured the quantity of hydrogen, and then I calculated the ratio between hydrogen and nickel atoms.
By decreasing pressure, yes? Yeah.
So thanks, Obama. Okay.